Hi, everyone. So yes, I'm Matt Heydeman, and I'm going to be giving a talk on this paper, which appeared recently with Jan Borg, Luca Alessio, and Joaquin Toriachi, who are in the audience in various physical and online capacities. I'd also like to thank the organizers for giving me a chance to speak. It's nice to have sort of a almost normal seminar after 2 years of rather unfortunate circumstances. So let's begin. Roughly speaking, I'm going to be talking about the Euclidean gravitational path integral and some recent developments and what we can say about that, especially in the context of AdS5. So the starting point for this might be something like the Bekenstein-Hawking formula for the entropy of a black hole. So the entropy goes like something like area over G Newton. And so it's a very large number, but there isn't, and it is quantum in the sense that it's somehow supposed to count microstates, but there's no real calculation of this that uses the gravitational microstates. So there's no path integral picture of this in some sense. So it's more of a prescription. And this can be improved a little bit by using the Gibbons-Hawking prescription, which is to say maybe something more in the grand canonical ensemble, where you might compute a thermal partition function by fixing some boundary conditions for whatever manifold I want to consider, and then summing over all manifolds that satisfy those boundary conditions, and summing in the sense of a path integral computation. The advantage of this is that it gives you some kind of saddle point approximation of what you might call the Euclidean partition function, and also tells you that you can compute one loop effects, and also maybe depending on changing the parameters or the potentials, different saddles might dominate. You can understand phase transistors, things like that. But the problem with this is that it's really still not, even now after many years of these things being proposed, it's really still not clear which saddles are supposed to contribute. You know, does this sum really converge? How do you actually compute the one loop determinants around each background? Am I supposed to include more things here that are outside the scope of gravity, and so on and so forth? It's not really clear if this formula makes sense. So there's at least some hope for doing Euclidean gravity, and that comes, again, even many years after these formulas were proposed. The reason why we still take these things seriously is because we do have a UV model that does give you some candidate microstates that these Euclidean prescriptions might be counted. So there's some UV completion in string theory, for instance, and well, in string theory, and in particular, AdS5 really gives us some precise observables that, at least when they're protected by supersymmetry or robust in other ways, you can make some kind of precise match between quantities in Euclidean gravity and dual boundary conformal. So we're going to be inspired by the fact that examples in string theory seem to work, even if we don't know how to make full sense of the Euclidean path, at least the starting point. So I'm going to be talking about black holes in higher dimensions and their quantum corrections to the path integral. So most of this will hopefully be review. So I'm going to be using Euclidean time. I'll still not use the pointer too much, but so these black holes will be have some periodic Euclidean time of length beta, and they'll asymptotically become something like AdS space or flat space. In this talk, it'll be AdS, but this discussion is general. They might have some spherical horizon if the black hole is rotating. The horizon might have some squash sphere topology. And in particular, we want to consider black holes that are not small black holes, but large black holes, in the sense that we'd like to take the mass to be very large. So in some sense, you're suppressing the quantum corrections to gravity, or naively, you would suppress the quantum corrections to gravity and the extreme corrections and so on. But we're going to use the fact that there's charge and rotation to scale these black holes to the extremal limit. And so when we scale the charges to be as the same order as the mass, the black hole temperature will actually go to 0. And essentially near the horizon, you'll develop an infinite throat that, as the temperature gets lower and lower and lower, becomes closer and closer to exactly AdS2. This is very familiar. Now, if we expand the mass and entropy around their extremal values, which are denoted by E0 and S0, we see that they grow like some characteristic scale times the temperature squared and the temperature respectively. So I wrote this as a gap scale, and sometimes you can interpret it as a gap, but in general, we'll see that it is not a gap in just a moment. So now this looks like it might be fine. We're just expanding what Gibbons and Hawking gave us. But the problem, one problem at least, was pointed out in this paper by these authors, including Al, who's in the audience. And what they pointed out was that black hole thermodynamics actually has to break down when the temperature gets sufficiently small for a simple reason, which is that a black hole emitting an average Hawking quantum, the Hawking quanta has energy that scales like linear in T. But you see that the black hole mass above extremality goes like something quadratic in T. So usually the quadratic will win, but at low enough temperatures, the linear can win. And so a black hole emitting a single Hawking quanta will change its mass by an order one amount. So it's hard to say that these black holes can be in equilibrium. So something about the thermodynamics has to change. And normally we're told that one should replace your classical formulas with something that's upgraded to a quantum mechanical formula. So there's another perspective on why this low temperature limit is bad, which is that the AdS region appears to be too trivial, at least for rigid AdS. So the old argument is that it can only contain ground states, doesn't support finite energy excitations. A dual CFT1 has to be topological only between ground states. This is an old lore. I put this paper, although I think that many people argued, even if it wasn't articulated in any specific paper. So I guess the sort of modern perspective is that we have to go back and revisit what it means to have the appearance of the AdS2 region, to take the temperature to 0, and what happens when you have this emergent SL2R symmetry. So that's the modern perspective, is that rigid AdS holography seems to be inconsistent. CFT1 is a little too simple, so we have to go just a little beyond CFT1 by including finite temperature effects and break the SL2R essentially. So the prototypical example is the SYK model. I think many people in the audience are very familiar with this, and I guess everything else I've said so far as well. So I'll just do a very quick review of SYK and its relationship to gravity. So I'll build the analogy on both sides. So in field theory, SYK is a large N quantum mechanical model that has in the infrared some reparameterization symmetry. And the dual statement is that there's some kind of gravitational system in AdS2. Well, not in AdS2, but it has an AdS2 solution. This gravitational system might not be Einstein gravity, but it has some kind of diffeomorphism symmetry, and that's sort of the reparameterizations. However, the SYK model actually spontaneously breaks the reparameterizations down to just the SL2R subgroup, which is like the global one-dimensional conformal group. And that's dual to the statement that picking the AdS vacuum essentially picks an SL2R isometry group for you. So the vacuum only has the SL2R, not the full diff. Now, when we turn on the finite temperature, this is sort of the new important insight, is that the finite temperature effects will now explicitly break the SL2R. And that's dual to the statement that finite temperature essentially deforms the AdS2 boundary. And this is sometimes called nearly AdS2. Maybe in some sense, nearly AdS2 is not just the metric anymore, but it has to include at least some dilaton, and it really should represent an AdS2 region being embedded in a bigger model. I think that's one good way to think about it. So in the field theory side, then, this soft mode that describes the SL2R breaking or captures the breaking of the SL2R is this Schwarzian EFT, which I'll write on the next slide. And the boundary mode on the gravity side, the extrinsic curvature at the boundary in this near AdS2 region, is also just the Schwarzian. So that's the dictionary. And what I'll say is that the SYK model directly is hard to build into any kind of UV setup, but the Schwarzian and the infrared physics appears to be sort of a universal feature. And we can argue for some specific version of the Schwarzian or some specific effective field theory based just on the symmetry considerations. And in this case, it came only from the breaking of the SL2R by finite temperature. So one of the points that I'll try to emphasize in this talk is that we're sort of arguing more generally that in some sense, we should find Schwarzian physics in all kinds of conformal field theories and not just the ones that are realized in these specific one-dimensional models. I think this perspective was advocated by Subir, among other people, that we should, additionally, we'll see in a moment that there's a gravity prediction for this Schwarzian mode as well, and indeed a prediction in a 10-dimensional gravity setup where the original AdS CFT correspondence was formed. So,
sorry, why do you say SYK is hard to build into a UV setup?
I meant something like, so in sort of these string theory models where you have intersecting grains, where you sort of have a derivation of AdS CFT. I mean, I don't think any is known right now, although one might hope that it may be discovered perhaps in the near future.
In principle, SYK is just free fermions perturbed by some interaction.
Right, I would say so. I guess the random couplings are not something one normally sees in string theory, for instance, but we can talk about possible ways to realize SYK models and SYK-like models in string theory. I think it's an interesting direction that's in progress as well. So, right. But for now, let's say that's our story is that we don't know how to build this directly. But we do know how to build these higher dimensional CFTs that we know are dual to higher dimensional AdS. So we'd like to see if there's a Schwarzian limit of this. Okay, so the Schwarzian derivative is some third derivative function that's kind of nonlinear. It looks very difficult to quantize at first glance. And the action is based on just the integral of the Schwarzian. Now, additionally, there may be additional G symmetries. So for instance, they might have reparameterizations of a group G, and that will be like adding a compact boson with a G target space to the action. So the vanilla Schwarzian I talked about before is just describing the broken SL2R symmetry, and that's realized in higher dimensions in terms of Reister-Nordstrom black hole in the canonical ensemble where we fix the charge. This gap here will become very important very quickly, and the gap question is whether or not there's a gap between the extremal black hole and the lightest non-extremal black hole. And you can see in the non-supersymmetric case, as well as in the minimally supersymmetric case, there turns out to be no gap. And in higher amounts of supersymmetry, there will be a gap. In the n equals 4, there's always a gap, and in n equals 2, it can depend on parameters of the model that we'll have to compute. So the number of supersymmetries is the one-dimensional supersymmetries. So in the case, one more thing that I should mention is that the coupling of the Schwarzian that I didn't write here because it depends on the relative coupling of the U1 and the Schwarzian, but the coupling will usually go like something like M gap, which I'm now rebranding to M SL2R. And this is the scale where the black hole thermodynamics broke down and we saw before. So the Schwarzian coupling and the Schwarzian scale is the same as the gap scale where we saw the problem. So in this particular talk, we're going to find, well, I'll give some background on the n equals 2 Schwarzian, and then we'll find through a bulk calculation, a detailed bulk calculation, that the AdS5 black holes in AdS5 process 5 dual to n equals 4 superconducting moles are described by a Schwarzian that has an emergent SU111 symmetry that's broken by the finite temperature effects. And then we'll compute the parameters of this Schwarzian. Okay. So let me give some details on the n equals 2 Schwarzian, since that's the one that will end up becoming important. So the fact that you have a U1R symmetry and thus a U1 reparameterization mode, which is dual to an abelian gauge field in AdS, presents some additional choices for us. So the action for the n equals Schwarzian is just the Schwarzian plus this U1 boson plus fermions, which are much more complicated to write. But because it's U1, we have choices about the radius of the compact boson, which I'll parameterize by this parameter R, as well as whether or not we want to include a theta angle type term in the 1D theory, and also the value of the parameter theta. So R is essentially the minimum R charge of any field, where 1 over R is an integer for supersymmetry reasons. And theta will be, if you want to preserve charge conjugation invariance, theta will have to be either 0 or pi.
I'm sorry, what is 1 over R as an integer? That means that's a fraction.
Yes, so R is a fraction and 1 over R is an integer. I probably could have said that differently. 1 over R must be an integer. And if you had too big of spacings between charge states, the supercharge always has charge 1. So if you have a charge at, in the spectrum of 1 and 5 or something like that, the supercharge should tell you there should be charges with 2 and 6. So that puts some constraint on whether R is an integer or fraction. Okay, so when you exactly solve the Schwarzian partition function using the techniques from Stanford and Witten or Thomas, Joaquin, and Herman, you'll find some rather complicated expression that involves a sum over, essentially a sum over fluxes of the gauge field, or a sum over saddles of the U1 boson, times a phase factor from the topological term, times the fermion one loop determinants, times the classical piece. Here I've introduced a chemical potential that goes like where I've absorbed the beta into the chemical potential. So just to briefly comment on the spectrum of this theory, there's two kinds of multiplets that appear. There's the short multiplets and the long multiplets. The short multiplets will have charge Z, and the long multiplets will have charge Z and Z plus 1 related by supersymmetry. Now, when the details of the Laplace transform essentially tell you that there's only a certain allowed range of charges for the short and long multiplets. And there are some R multiples of Z that might get shifted by the theta angle. And the BPS sector in particular, there's a fairly stringent restriction on the allowed charges. And the density of states in the BPS sector will always be a delta function times some phase factor times the extremal entropy. And for the long multiplets, you'll get something like the characteristic sinh root E over E that we see in the Schwarzschild. I should say here that there's a heavy side theta function here that tells you that this sinh function may start at a particular gap scale, where that gap scale is this E gap. So maybe a takeaway message from this slide is that depending on the value of R and theta, and the fact that this charge range is very restrictive, you might find, for instance, that the spectrum doesn't have a gap, for instance. If a Z-Schwarzian equals 1/2 charge is in the spectrum, that means the gap is just 0. Additionally, if you set the parameter of R to be some random number that's not 1, you find that the index exactly vanishes. So the details of the spectrum, the extremal entropy, and the quantity protected by supersymmetry actually depends on these discrete parameters. They're not just some extra things we can stick into the formula, and you wouldn't really see their effect. I believe if you just did a semi-classical analysis and found I had an AdS2 theory with a U1 gauge field, I wouldn't necessarily see that these additional parameters are important. So one of the big tests is to show where these come from Tindy. So one final question before I get to the meat part is essentially, do non-supersymmetric extremal black hole microstates actually exist? And what does it even mean for them to exist? I think this question was posed and partially answered in our previous paper. So I stole this slide, from the previous paper. So this phi R should be this gap scale as before, and these plots are actually for Reister-Nordstrom and not for the 10D problem, but essentially in the non-supersymmetric case on the left, just for Einstein gravity, the quantum corrections drive the density of states as a function of energy to 0 at low energies. And they don't give you this e to the S0 density of states you would have hoped to find from Hawking's area formula. But in the supersymmetric case, you find that essentially in some charge sectors, you find that there's a miraculous cancellation of this density of states that gives you exactly back the extremal degeneracy. And then also, well, the cancellation gives you a gap, and the supersymmetry gives you this extremal degeneracy. So on the left-hand side, we don't exactly really know if we should take this spectrum seriously all the way down to 0 energies. But we know that even if there's a non-perturbative completion in S0, it might resolve the individual microstates and give you some states exactly at 0 energy. We might not want to call these states black holes because the black hole degeneracy goes to 0.
Well, what I thought you were going to say was that we might not call them extremal.
We might not call them extremal, yeah. This calculation is based on an extremal plot.
But presumably, that red curve you've drawn on the left becomes unreliable when you get close enough to 0.
Yeah. Close enough to 0, this curve is not reliable. So maybe you shouldn't trust the Reister-Nordstrom solution and its Schwarzschild correction. The extremal Reister-Nordstrom solution. You think that we maybe shouldn't call them extremal black holes at least?
Your work strongly suggested at least there's no ground state black hole degeneracy.
Yes, I would agree that there's no ground state black hole degeneracy that looks like extremal Reister-Nordstrom. Yeah.
But there's still a prefactor of e to the S0 from the whole curve.
Sorry. So yeah, the e to the S0 I put on the left-hand side here. This is what you would get if you just followed the classical formula down to 0, right? And the quantum corrections tell you that, oh, actually, when you include the beta one loop determinant correction along with the classical Schwarzschild result, that really, in the non-supersymmetric case, the degeneracy does go to 0. So there's an e to the S0 prefactor, but it's times a function that goes to 0. So
I thought you'd want to say that it gets much less than e to the S0 within the validity of your approximation.
yeah, it gets
Extrapolated beyond your calculation, I think.
Maybe the statement I said is sounding a little too strong. We can't really trust the calculation down here. There's going to be all kinds of non-perturbative corrections that resolve the individual microstates and maybe change the behavior at exponentially small temperatures. That's definitely true. But then at exponentially small temperatures, we're not sure. Clifford?
Finish your thought.
Oh, okay, well, I think you were maybe going to help me give an answer in a moment, but I was going to say that exponentially small temperatures, we shouldn't trust just JT gravity, or well, models that reduce to JT in the Schwarzschild and so on. So that's the only statement I'm trying to make. Yeah.
Well, as you and I have discussed, you can construct non-perturbative completions of that regime and see the effects of microstates.
Yes, I agree.
And you can follow, if you calculate the right thing, you can follow the thermodynamics smoothly all the way down to t = 0.
Yes, I agree.
And you can follow the entropy and see that you have some amount of, what that's telling you about is the amount of entropy above S0. And then you land on, t = 0, and the excess entropy goes to 0. But you still have that S0 in the sense that Sabir just said, there's the e to the S0 factor coming along for the ride, which tells you you have that extremal entropy built in. So I'm a little confused about the expectation that you should see in the density of states that S0 degeneracy. I'd say it's already built into the model, and all that density of states tells you about is what happens beyond the extremal entropy. That's how I would read it.
Okay, I guess I was going to say that in some sense we have in mind a higher dimensional black hole where we don't know how to include all of the corrections. So in JT we have some idea of how to include all the higher genus topologies, but in some higher dimensional model we really don't know what to include. So what I'm saying is I only, in a higher dimensional black hole, I only can see the Schwarzschild. I don't know how to include the higher topologies directly because there are other effects that might compete with the higher topologies. So
I agree, but I'm not talking, the picture I gave has nothing to do with the topological expansion. It's beyond that. It reproduces that perturbatively, but there's a statement you can make independently of any topological picture that aligns with what I said.
But, well, okay. I mean, the density of states that one gets from the Schwarzian mode is a cinch, which goes to 0. That's perhaps the only statement I'm making is that you shouldn't trust the calculation at 0, and you have to include other stuff.
Sure.
That's
we agree. Okay,
yeah.
good. I thought you were trying to say
I agree
something.
with Clifford that if you take a random matrix point of view, the exponentially large degeneracy is completely not expected.
Right.
But the fact remains that in previous calculation of black hole entropy using supersymmetry, there was a degeneracy. And from that perspective, the right-hand side is the one that's surprising, not the left-hand.
Indeed. Yeah.
From random matrix point of view, you wouldn't expect this huge protected sector. Exactly. And it just so happens that the protected sector, this arrow here, exactly meets up where Hawking's calculation is. So previous people who were doing this calculation thought, well, we can only do the computation right here and we get Hawking's answer. Therefore, black hole thermodynamics works and is not subject to additional problems. But I agree that it should be surprising. The right-hand curve is surprising, especially since we now know that there's something that fills in the classical answer and the quantum corrected answer, and it's not maybe what one would have expected. So that's what I was going to say. And the second underlying part is that this should be thought of as a surprising prediction that gravity gives you some discrete spectrum, or at least some piece of a discrete spectrum, and then also this gap that's only polynomial in the entropy and not exponentially small. Like one would imagine that there would be exponentially small spacings, but the gap is something that's polynomial. So, okay. So these plots are important to spend the time on because we're going to get very similar ones for the AdS5 case, but I should really move on because okay. So our central goal is to take what we just learned about the n = 2 Schwarzian and apply it to the 10-dimensional black holes in AdS5 process 5. So we're going to consider the black hole in the asymptotic AdS space. By AdS CFT, these black holes are dual to heavy operators and n = 4 super nulls. They're labeled by some mass, some spin, some R charges. Now, so for some large values of the charges, the black holes, for some values of the charges, the black hole is BPS, which means it's extremal and supersymmetric. And the BPS states have some exact counting in string theory by doing an n equals 4 super-Heydeman calculation. So then this is the starting point. We then go to the near BPS limit. We deform away by breaking, by turning on the finite temperature effects I discussed before. And then essentially we'll move the temperature and potential away from the BPS value. We'll need to determine the ensemble from which the BPS states are captured. And then we'll use the bulk geometry to find which Schwarzian we care about, and also compute the parameters of the Schwarzian. And this will allow us to quantize the Schwarzian using the previous results in the previous slide. And then using the result for density of states, this will make a prediction for the near BPS heavy operators on equals 4 super-Heydeman. A statistical prediction in the sense of what I was describing in the previous slide. We don't necessarily get an exact resolution of the spectrum, but we get a statistical prediction of where there's going to be a large number of states and where there's going to be a small number of states controlled by non-perturbative fractions. Okay, so this is the picture of the setup. So we have an AdS2 fibred over an AdS3 with rotation, fibred over an S5. So this is asymptotically an AdS5 space, but near the horizon, it looks like an AdS2 cross S3 cross S5. For technical reasons, we'll take the rotation on the S5 to be equal charges, because you'll see in a moment the metric is very hard. And the point is that a big reason why we're talking about the 10D geometry is that this is really not in some sense an intrinsically 2D calculation. The Schwarzian parameters that set the spectrum are, you're required to sum over bundles in some sense. Additionally, the data is fixed by the 10D solution. So as I said, we'll fix the boundary conditions, we'll fix some charges and some chemical potentials. The KK modes will not produce temperature dependence. So at low enough temperatures, we're capturing the dominant temperature dependent contribution. Additionally, we won't include the log area corrections. In principle, the one loop determinants of matter fields can be computed in this background, although as I understand it maybe is challenging. I'm not sure if anyone has exactly done the full calculation all ascend. There are arguments from the Cardian limit. We also will not include higher topologies, D-branes, orbitals, other kinds of stringy effects. I know a lot of people in this room, as we've discussed, have found a lot of exciting things coming from the higher topologies. But again, I don't know how the higher topologies compete with other non-perturbative effects. So we won't try to include at this level. It's hard to see how to include them in a consistent way. So there are also technical reasons why we would have trouble doing higher topologies that come from the large amount of supersymmetry. Okay, so I should run through the bulk solution very quickly. So we're going to start with the type 2b supergravity action. We're only going to turn on the metric in the 5 form, which is self-dual. So this action is secretly 0, but we'll ignore that for a moment because the equations of motion are fine. We're going to, for technical reasons, reduce to an AdS5 black hole. So we're going to do a Kaluza-Klein reduction on the 5 sphere. The metric will have equal angular momentum on the S5 because the metric is complicated. And so that's gauge field A here that appears in the metric. The 5 form is self-dual, and within our conventions, that will set the AdS radius to be 1 in these units. So doing this dimensional reduction lands us on something called 5-dimensional minimal gauge supergravity, and that is has a metric, a single abelian gauge field, and a complex gravitino. There's no scalars because of the charge configuration that we chose. Also note there's a Trent-Simons term. This gets generated from the self-duality of the 5 form in 10D. Finally, the whole action is proportional to n squared. So every time you see a 1 over G5, just think that that quantity is large and of order n squared. So the black hole solution is very complicated. I put this up here, it's more a picture of the solution, and you shouldn't think too hard about it. But it's just to show you that already in the case where we set all 3 of the R charges, there's 3 because there's 3 cartons of the SO6 on the S5. So even in the equal R charge sector, the metric is very complicated. The most general one is it's hard to even check that it solves the equations with the computer. So your intuition for this metric should be that it's some sort of generalized AdS Kerr-Newman. It depends on 4 parameters, sort of a mass, charge, and 2 spins. And we should also note that since we're doing Euclidean gravity, we're going to wick rotate the time coordinate. I wrote it in the lens, and you can see, but we're going to wick rotate the time coordinate. And then the periodicities of various chemical potentials will, the periodicities determine the chemical potential. We essentially need smoothness around the Euclidean horizon. So the gauge field will have some asymptotic value, and that will need to be smooth. And then the angular momentum will also be determined by the smoothness. And the Euclidean horizon is at the largest positive real root of this expression. So the charges and potentials, as I said, there's a recipe for constructing them. Again, their exact value is not very important, just pointing out that the charges go like 1 over G5, so they're large n squared order n squared charges. So in the grand canonical ensemble, we might try to evaluate the partition function by just taking the exponential of the classical action. Of course, there can be many other saddles. There can be one loop determinants, non-perturbative sections, and flux sectors. The flux sectors will become important in a moment. When you evaluate the on-shell action, you get some explicit expression, and one can also evaluate the entropy. And importantly, black hole thermodynamics works because the on-shell action you compute carefully is given by this quantum statistical relation. So the on-shell action gives you the free energy. Okay, so there are various limits of the black holes that we can take. We can take sort of the non-supersymmetric limit or the supersymmetric limit, and then we can have 0 temperature or finite temperature. So the case where it's non-supersymmetric or finite temperature is just the generic black hole. If we don't preserve supersymmetry but turn on some temperature, we have an extremal black hole that just happens to be non-supersymmetric. If we make it supersymmetric and extremal, we get what I will call a BPS black hole. And anytime in this talk a quantity is BPS, I will put a star next to the formula. And the charges in the BPS case obey some nonlinear constraint. The final quadrant I need to fill in is this one, which I'm calling the non-black hole. And this one is formally in Euclidean signature, you can set the parameters such that T is greater than 0, but the solution is supersymmetric. And this might violate your intuition about a BPS state having the lightest mass for a given set of charges. But the point is that these black hole solutions have closed time-like curves in Lorentzian signature. So we won't consider them as black hole solutions. They might be dual to states in n equals 4 super-Young mills, but we won't think of them as black holes, and they won't play a role in this.
You
So
think they might be dual to states, what you mean the states with those quantum numbers might exist?
yes, that's what I mean. Yes, in the UV boundary theory, they might exist, but we don't want to call them black hole solutions, even though you have some metric and you can set the parameters such that this is true, but it's sick in Lorentzian signature. So those values of charges might exist in the dual theory. And I don't think this point is particularly well understood.
Do you also have solutions where, if I remember correctly, in a simpler case, you can get 0 temperature solutions that no longer have horizons?
You mean when the horizon shrinks to 0? So all of these black holes have finite horizon area. That's the problem.
Okay,
there are small black holes, and they're completely not in this.
No. When you have these charges, I just remember from work in the 90s that there were these what we called superstar solutions that you realize they're built out of you can build them out of rat brains. They're perfectly sensible solutions, but they're not black holes anymore. I just wondered if they were part of your map of solutions and whether you have.
I don't think if they don't realize that Bukowski-Real solution, they're not in this table. That's the simple answer. Maybe a better physics answer is that these are the solutions that have entropy of order n squared. So if the star solution built from D brains doesn't have entropy of order n squared, it'll be subdominant in the grand canonical ensemble. But as I said, I would love to include as many corrections as possible. And these black holes are sort of seemingly the biggest contributor to this, I think, extreme entropy. Okay. Right. So we want to say something about n equals 4 super-Young mills with these black holes. So they're dual to 1/16 BPS states on S3. And so you can break the global superconformal group PSU224 down to some compact carton. So we'll label states by 2 spins and potentially 3 R charges. So essentially you're breaking the n equals 4 symmetry to n equals 1. And so you have an n equals 1 vector and 3 n equals 1 chirals that have equal R charges over 3 U1s. And the chiral multiplet has top component charge 2. And those choices set the numerical factors in the partition function. So this is the grand canonical partition function of n equals 4 super-Young mills. But of course, we want to think about some gravity way of computing this. But as an important comment, if we take linear combinations of the chemical potentials such that they satisfy some sum to some imaginary value, it's equivalent to inserting -1 to the f in the trace. So this quantity is actually the superconformal index, and it's been studied by many people over the years. So the superconformal index is protected in the sense that it doesn't depend on beta and it doesn't depend on the couplings. So you can compute it at weak coupling. There's various techniques and strategies for computing it. And the superconformal index has in recent years, due to a number of heroic calculations, been matched at leading order of the large N expansion to the supergravity action. So this is a precise statement that there's some exact quantity you can compute in the field theory. It's protected by supersymmetry. It exactly matches the black hole entropy. But there's a caveat here, which is that the index is not in general equal to the ground state degeneracy, because it only counts the difference between the bosonic and fermionic ground states. So first of all, it misses the finite temperature effects, which is the whole point of this talk. And also there's no guarantee. There are arguments that the index should agree with the degeneracy, but I think there's no guarantee that that should be in general true. And I think it was initially believed that maybe there were cancellations, and that was later shown to be not true at leading order in N. So what is it that we want to ultimately compute? We want to compute actually the partition function and not the index. And when you write it as a trace in with some microscopic model in mind, the charges are integer. So if you shift the chemical potential by some integer multiple of beta, this is just trivially invariant under shifting. Now, you might ask, why would we want to shift chemical potentials by imaginary integer multiples? Well, the idea is that we want to, in gravity, approximate this trace by some sum over saddles. And when you pass from a trace with the exponentials of the chemical potentials to a sum over saddles, that sum is not necessarily invariant under these shifting of chemical potentials. So it's hard in the gravitational sum over saddles, it's hard to see the discreteness of the spectrum. So one way to fix this that was, I think, explained very nicely in this paper here, is that we should actually sum over the classical action corrected with a one loop correction, but then sum over shifts of these chemical potentials subject to some constraints so that the formula is actually invariant. So in the bulk, these shifts have a nice interpretation. They're smooth geometries where one starts with the black hole solution in grand canonical ensemble with some potentials determined by smoothness. Then you shift those chemical potentials by imaginary values, which is like turning on different asymptotic boundary conditions for the holonomy of the solution. And these are saddles that are subleading, but they're not, they're still of order n squared, but they're subleading compared to the dominant black hole saddle. The point is that at low temperatures, these new solutions will become physically important, and essentially they'll be capturing ultimately the U1 mode from the JT gravity point of view, where we had to sum over flux sectors to get a reasonable partition function. So we're going to sum over both flux sectors using this n equals 4 as the inspiration. So we're instructed to sum over shifts. We're going to write Z in a suggestive form, identifying some pair of supercharges that relates to energy and the R charges, angular momenta. And the key point, though, is that the trace that we've written so far, it includes black hole solutions that had unequal angular momenta on the 5 sphere. And I told you that the metric was horrible already, even with the equal R charge case. And right now, our ensemble contains solutions that are even outside the scope of what we were talking about. So on a technical level, we're going to need to pass to a mixed ensemble. Essentially, we're going to fix some charges and then fix some chemical potentials so that we isolate the black hole solutions that we've discussed already. So we'll just introduce several new charges along the way. I should click through this pretty quickly. But so we'll introduce some combinations of angular momenta and R charges, and these Qs, we're going to set them to 0 because they're the differences between angular momenta. So we'll further introduce some additional chemical potentials. And the reason for introducing all these variables is essentially we decouple this sum over constrained integers into, upon Laplace transform and going to a fixed charge sector, we'll get in the end the box formula, which is a sum over a single unconstrained integer, but now we'll evaluate the action in some mixed ensemble. And the reason why we do this is because this is where it's easiest to compute the Schwarzschild corrections. It's not the most general ensemble one might want to consider, but it's the one where we can easily identify the nearest extremal. Okay, so I think actually most of what I've said so far could be discussed roughly in the context of classical gravity, but now we'd like to take the low temperature limit and bring back in the Schwarzschild corrections that I discussed in the first couple slides. So are there questions now, or should I proceed to the low temperature limit? Okay. So the near horizon geometry and the extremal limit. So we're going to take the low temperature limit and new symmetries will appear and they'll be broken by the finite temperature Schwarzschild limits. So we'll analyze the symmetries of the model exactly at extremality. We'll compute the Schwarzschild parameters and then we'll bring those quantum corrections back in. So just to pass the near extremal limit, we will perform some diffeomorphisms, then take the near horizon limit of the zero temperature solution. And this will lead us to a metric that looks like AdS2 fibered over S3 cross S5. And so there's some explicit AdS2 metric that you get out of this procedure, where the AdS radius is now some combination of the charges of the. But just for technical reasons, I set the two spins to be equal. So to analyze the bosonic and fermionic symmetries, so we find what superconformal algebra, the Schwarzian, is breaking, we'll just find the killing spinors directly in 10 dimensions. So the killing spinor equation only involves the gravitino in 10D. This epsilon will be some type 2b killing spinor subject to some chirality conditions. And with a bit of work, one can show that the following two killing spinors solve this equation. So the bottom spinor, epsilon 2, that was the one that was present even in the original black hole geometry. That told you that when you tune the charges to extremality and BPS, you had they were 1/16 BPS. The second set of killing spinors are the conformal ones, and they show that there's a doubling, so there's sort of the enhancement of supersymmetry, which is the super partner of the enhancement of the conformal symmetry in the near horizon region. So when you can compute the killing vectors associated to this set of supercharges, and when you look in the bosonic sector, so the D, this is the scaling, and then these are essentially P and K. So the D, E, and K I've written here, they satisfy an SL2R subalgebra, but there is an additional killing vector, Z, and that one is essentially a U1, it commutes with everything. And the Z, if you look carefully at the expression, it's a combination of equal rotation on the 5-sphere and also equal rotation on the two angles of the 3-sphere. I chose equal angular momentum there. So what this is sort of telling us by, I should say that also with the killing spinors in hand, you can associate a supercharge to them and compute their commutation relations, and you'll find the correct expressions for the n=2 superconformal algebra. So these are the commutation relations along with the ones that I didn't write down. These are the commutation relations of the SU 1,1/1 superconformal algebra. So that was associated to the n=2 Schwarzian, which is why I went to the trouble of explaining the n=2 Schwarzian in the beginning. And we can see that the U1 boson in the 1D theory, that's dual to a U1 gauge field in AdS2. And that U1 gauge field you can think of as a Kaluza-Klein gauge field from reducing all the way down to 2D on this product of spheres. Okay. So now we want to expand the action to read off the coupling of the Schwarzian, this M gap scale. And some other parameters we'll see in a moment. So to do that, we'll fix the two chemical potentials and then fix these two funny charges, which have explicit expressions here. And then we'll do the expansion. So we have the potentials in terms of R, Q, A, and B. So we want to expand all the potentials in terms of these variables while always making sure to keep these guys fixed. And you have to go into second order. And the result is that the mixed canonical ensemble, just expanded at low temperatures, has some extremal, it has the sort of ground state energy of AdS. It has S star, which is just the extremal entropy. We called it S0 in some previous slides, but this is the BPS entropy. There's an additional term R star that couples the chemical potential alpha, which tells us that there's sort of an emergent R charge at low temperatures, which is given by this R star. And then there's also this temperature linear dependent correction, which which one can compute the value of this 1/m SU111. A similar expression was obtained in this paper, although it wasn't exactly clear what ensemble they used, and your answers are actually fairly dependent on what ensemble you choose. So we made it very clear in our paper which ensemble was the one that gave exactly the Schwarzian limit, and then computed these parameters from the action. Okay, so we're going to finally put everything together now. So in the low temperature action, we found what the classical part of the action was. We found the emergent symmetries by looking at the near horizon throat region at 0 temperature. And we found how to write Z as a sum over these shifted saddles, these shifted flux sectors. And we kept the sum because I told you you wouldn't get consistent answers if you didn't include this sum. And so you can see that the sum here, the sum over integers enters in this prefactor like n squared. And so you see that these saddles will be subleading, but when the temperature is very large, they're all going to be roughly the same action. So we really should include at least these sum over saddles. You might want to sum over other things, but this is sort of a minimal set that you should sum over to reproduce the Schwarzian and get consistent. I've left the one loop determinant because we haven't computed that yet, but we will in a moment using the results from the previous slides. So the R star I said, that showed that the UV and the IR charges had a mismatch, and the one loop determinant will compute. But otherwise, this is the n equals 2 partition function. So it came from putting together sort of the 3 big ingredients from the 10D solution that we understood. We used a little bit of input from n equals 4. We used a little bit of input from this AdS2 geometry, and we use a little bit of input from the black hole thermodynamics, and that's what determined the form of this. I should mention that because all these charges have really complicated expressions, it's sometimes nice to sort of take a scaled limit where we set the 2 spins to be very large. So this is some double scale or some kind of scaling limit in which we additionally fix the charges to be very large, and then the extremal entropy, the charge, and the coupling look much more simple. So as I said before, this partition function is one loop exact, and we use the results I said, I already cited this, but so essentially all we needed was the one loop determinant, and that one loop determinant, essentially the alpha dependence here really comes from the fermion zero modes. So the supersymmetry seemed to play maybe sometimes an ancillary role in this analysis, but these one loop determinants are very much dependent on the fermions being there. And you get this cosine is secretly encoding the sum over the states in the supermultiplier. And so we have the form of the answer is again this phase factor that depends on the R star charge, this zero temperature, the AdS vacuum energy, the sum over saddles, the one loop determinant, the classical piece, which has S star plus the temperature dependent Schwarzian correction. So this is the final form of Z. And in particular, I said at the beginning that there was this big family of n equals 2 Schwarzians. But we see here there's no topological term present because there's no phase factor, and the R parameter is 1. So one interesting thing about this is that there's no supersymmetric SYK model that realizes the R equals 1 theory. So that's an aside. If I compute the index, that's essentially taking this formula and setting alpha equals 1/2. I recover e to the S star, the extremal entropy, which is what people obtained from a pure n equals 4 super Mills calculation, with this additional phase factor, which essentially says that depending on the value of R star in this ensemble, depending on the value of R star that I chose, the ground states are either all bosonic or all fermionic, and there aren't cancellations to this order n in the index. So I think this is maybe a gravitational explanation, at least in part, for why there's no cancellations. Okay, so Laplace transform, we get a density of states. I'm gonna work in the R equals R star sector because otherwise the formulas are more complicated. But I'll show a bunch of plots on the next slide to explain. So the key of this is that we're going to take the n equals 4 super Mills data, and then we're going to compare it to the Schwarzian data. So the n equals 4 super Mills will be labeled by essentially a delta and an R, say, for the scaling dimension and the equal R charge sector that we're considering. And on the Schwarzian side, we have the BPS mass, which is just this combination of charges, plus the Schwarzian energy. This is the energy that you would get by just looking at the Schwarzian mode. So this couples to the temperature, as well as the Schwarzian R charge, which is the charge that couples to this alpha potential that I introduced. So then the final form of the density of states has a delta function at the BPS bound, as well as this sinh root E with a step function, and a step function that starts at the gap scale. So this is written in n equals 4 variables. So we derived this using the Schwarzian and using gravity, but this formula is, everything in this formula should be n equals 4.
I'm sorry, what do you mean by data on the left-hand side? You're using it twice, but when you were talking about it, you mentioned it was Schwarzian energy instead.
I just mean the labels for the states. States are labeled by this information, and so that's all I meant by data.
So data, you don't mean like data points as an experimental data now?
I would love to test this in an experiment. That would be probably the greatest moment of my life. Unfortunately, we don't have access to a 10-dimensional sector. So no, I simply mean the labels for the states. The states carry charges, and these are the labels. And the labels that we use for the Super-Yang-Mills theory are not the same as the labels we use for the Schwarzian theory. We need to build a dictionary between them. And then the density of states that I use, this was obtained from quantizing the Schwarzian, but it's written in terms of the n=4 charges. Yeah.
Yeah, I want to ask what the U1R of the Schwarzian is. So if I understand correctly, your thing R is the sum of the internal charges in the S5.
Yes, yes.
And R star is the particular charge that this black hole carries.
Yes, yeah. So you can read this formula as if you're thinking about it in the Schwarzian side, then the thing you call the Schwarzian charge is R minus R star. Or you could read it as from the n=4 side, an n=4 state with charge R is mapped to a Schwarzian state with shifted by R star. So maybe the best way to think about it is to rewrite this Z Schwarzian equals R minus R star.
Right, but I would expect that as I increase R, I continue to have a BPS state, right? That should be BPS states with all values of R.
On the n=4 side. In this ensemble.
Yes. Okay, I think the point maybe you're going to say that they will not be black holes, or they will not.
Yeah. So there maybe I can show you the plots, and that might at least we can refine the question because it's a little hard to interpret this formula. So there's three different plots here, and maybe the equation that was on the previous slide is this one in the upper right. So what I did was I fixed R equals R star, which is equivalently saying I want to look at states in the Schwarzian with Z = 0. And the Z = 0 Schwarzian states have two pieces, right? They get contributions from the BPS sector and the non-BPS sector. So the BPS sector is they all have Z = 0, and those have e⁻⁻⁴ degeneracy. And then the non-BPS sector starts at a spacing of delta gap. And if you saw on the previous slide, sorry, I'm already going back here, delta gap goes like 1/n² times this complicated combination of things. So this gap is closing as a polynomial in n², but it's not exponentially small in n². So I'm looking at Schwarzian states of fixed Z Schwarzian = 0. And in that sector, there's two different pieces of the spectrum. If I chose Z Schwarzian to be non-zero, so when R is not equal to R star, then the extremal degeneracy disappears. So I didn't write the formula corresponding to the lower right plot on the previous slide. But what happens is that when the Schwarzian R charge is not zero, when you look at states with the non-zero R charge, the extremal degeneracy disappears completely. The thing that we call the, oops, sorry, oh no. Oh, sorry. So the thing that we call the lightest black hole, it starts at some value delta extremal, which is determined from the parameters on the previous slide, and it just gives you a continuum above that, and there's no gap here, and there's no ground state degeneracy. So yeah, maybe my point is that even when we're in the supersymmetric theory, we look at the supersymmetric Schwarzian, we looked at an ensemble where we had near BPS effects. Even there, depending on what sector of Schwarzian charge you're looking at, you may or may not have a gap in a BPS degeneracy. So the existence of the degeneracy in the gap is actually pretty non-trivial from doing this Laplace transform of the partition function, I would say. And I think that the plot on the left, the large plot on the left, kind of puts together these two plots on the right in a phase diagram. So the red line here, that's sort of the unitarity bound. You can't have any states that lie below that because that would badly violate the BPS condition. On the x-axis, you have R minus R star, which is essentially the Schwarzian charge, right? So when Schwarzian charge is 0, that's this black point here. This black point corresponds to this spike. And then the gray line here, the black line, that corresponds to the quantum corrected beginning of the extremal states. So you have the black line is at any point on the black line, not at this dot, you're essentially starting at some point delta extremal, and then the gray line that extends above it is the continuum that extends above it. So all these points here have some spectrum that has no gap and no BPS degeneracy, but they do have a continuum that goes up on the vertical, except when R equals R star, then there's this whole point, which is the extremal degeneracy, there's the gap, and then there's the continuum still above that. Now the blue line, the last thing that I didn't discuss was the blue line. The blue line is what you would get from a sort of naive semi-classical expansion. The blue line is where the extremality bound is, rather. So the blue line is the extremality bound in the semi-classical expansion. And you can see that the blue curve and the black curve do not agree, obviously. And but what's funny is that the quantum corrections shift the extremality bound down when you have positive R minus R star, but they shift it up when you have negative R minus R star. I don't have a priori a reason why it would get pushed up or down depending on the R charges, but it's very interesting that there's some quantum corrections to the extremality bound that come from these sort of subtle low temperature effects from Schwarzian. And this may be related to some kinds of discussions of the weak gravity conjecture where people talk about black holes that are approaching extremality and then do quantum corrections, change the naive classical prediction. And here we have a very sharp statement that that is the case. Okay, so I think I'm really only have one slide left. Well, I have a couple. Yeah. How much time do I have? Like 5, 10?
10 more minutes.
Okay. All right. Okay. So these plots are maybe a little bit less illuminating, but these are plots of the thermodynamic potentials. In particular, the mass, which I'm writing as delta, and the entropy, which I'm writing as S. So the top set of plots is the mass and the entropy for R equals R star, the case where we did have the supersymmetric set of states and the gap. And so you can see, and the blue curves are the classical, semi-classical prediction, and the black curve is the Schwarzian prediction. So in the blue curve, essentially when you see that, well, I guess it's not so clear from this picture, but this problem that we had, where we had mass scaling like t squared, but Hawking quantized scaling like t. There's a crossover at low t. This is actually, I didn't plot the t linear on this plot, but the Schwarzian correction actually always pushes you below this problem where black hole thermodynamics would have showed up. So that's at least a partial resolution to black hole thermodynamics at low temperatures. The entropy, when we had that supersymmetric version, the entropy meets up at the extremal bound, but it's always lower in the Schwarzian, and then it meets back up at S star, where S star is again the BPS. But when we go to an R charge sector that doesn't satisfy R equals R star, or sorry, Z Schwarzian equals 0, then the mass is noticeably different. We don't have we have a gap now in the mass. And then also in the black curve, we see that in the Schwarzian theory, the entropy goes to negative infinity. So that's the statement that the density of states is going to 0 there, which means that we need to include some more microscopic effects so that the density of states remains finite as t goes to 0. So we discussed this already, that we shouldn't trust the curve that goes to 0 in the density of states. This is sort of a restatement that we see the entropy has a problem. So yeah, so what I mean is that, yeah, of course, down here we need to fix the calculation with extra contributions. Okay, so I guess I have 10 minutes, but maybe I'll do this slide quickly. So in AdS5 process 5, we have the parameter n, which sets, roughly speaking, the Planck scale, and we have the parameter lambda, which sets the string scale. And these are a priori two different things that you can dial, because the AdS CFT dictionary relates n and lambda in this way that I've written. So it's actually known how to correct the type 2b supergravity action with the first correction from string theory. So there's some alpha prime cubed correction to the supergravity action. And we're going to ask, does this correction from stringy effects change the Schwarzian answer? So the caveat is that this is only leading order in alpha prime. And the technique is that we take this action, which it's essentially the biotensor to the fourth or r to the fourth plus a huge number of terms, which it was written sort of abstractly and then written a little bit more explicitly and then written most explicitly in this paper by Santos. And he did the trouble, went to the trouble of evaluating the Gopkovsky-Rial black hole that we've been considering, evaluating it on the correction to the action. And to leading order, this is sufficient so that the solution doesn't back react by including the string effects at this order in alpha prime, but the value of the on-shell action does back react. So one can explicitly see how the action changes when you include this string correction. And to summarize, all that it does here, it doesn't seem to invalidate any of the near horizon analysis. It doesn't seem to invalidate most of the thermodynamics and the arguments about the saddles. The only thing that it does is it shifts the value of that MSU111. So it shifts the Schwarzian coupling by an alpha prime dependent amount. And so in particular, it shifts the gap scale, and it'll further depart from the classical value. So I chose equal angular momentum in the scale limit, but you can see that the gap scale is now the delta gap that we saw before, corrected by some 1 over a TÜV parameter to the 3 halves. So
Curly J is the angular momentum. What is curly J?
Curly J is the sum of the angular momentum in the R chart. So I said J1 equals J2 equals yeah. So it's some linear combination of those. Right. So at the next order in the string coupling, one has to take into account the background of the action on the metric. It's not really clear how to do that. It seems like it might be challenging. But this at least shows that somehow the Schwarzian is robust from including corrections that go beyond just Einstein gravity. It's at least an example of that. Although you might ask, if I made the TÜV parameter really big, what happens as they really start to go to weak coupling in the gauge theory? That's really not clear.
Is it clear why it has that particular J dependence?
Why it has that J dependence? So when you basically this W evaluated on the solution is a pretty complicated combination of the charges. I couldn't say off the top of my head. We can go back and look at what.
I mean, naively, the correction should be alpha prime over some radius, which would be the AdS radius that would be just lambda. For some reason, there is an additional suppression factor.
Wait, so I guess in some sense, this J is a function of the A and B, the rotations, and the AdS2 radius is a function of the A and B. So they're not the same function, but there's sort of one numerical parameter hiding here that.
But does that mean that when J is very large, the radius of the solution becomes larger than the AdS scale?
Yeah, I'm not sure. Maybe if we looked at the explicit formulas, we might have some idea. But you can definitely ask when this correction dominates over the Schwarzian correction, and we say a little bit about that. Let's see. So to conclude, I guess I'm just about out of time. So we studied quantum effects in the gravity path integral. And we use effective field theory arguments looking at the symmetry breaking for these supersymmetric black holes and the supersymmetric geometries. And we think that it's useful in both gravity and in field theory, in the sense that we know how to account for the low temperature fluctuations on the gravity side. And we made a prediction on the CFT side. So I didn't find any Schwarzian sector of n equals 4 superunit nulls, but that might be a future direction. Essentially, AdS-CFT gave us a prediction for the spectrum of heavy operators, and the large amount of supersymmetry and the particular values of the parameters that we found from the Bolt solution led to, at least in the sector R equals R star, it led to I should have said large extremal entropy and a gap. The gap is small, the entropy is large. But we also have something to say about the unprotected operators. And to figure out some field theory calculation from those sounds very challenging, because it sounds like a strongly coupled gauge theory calculation. Not just strongly coupled gauge theory, but we're also looking at a sector of operators whose charges are order n squared. So they're some of the heaviest operators you can make in the field theory. So it might be hard to
have discussed some kind of effective hydrodynamic like theory for such operators.
Yeah, so there's a large charge expansion, and so there might be some large charge hydrodynamics that could describe this. And then you might also have some sort of low temperature Schwarzian-like hydrodynamics. So maybe there's some effective field theories that can capture this this behavior. It might be hard to do directly in any sport super.
It might be that it's a constraint for those theories.
Yeah, it's I think if you believe that the gravity answer gives you some kind of statistical prediction, then some hydrodynamic theory maybe should agree with the gravity answer. I mean that seems reasonable, but I don't think we thought too much about that direction, but it might be interesting to discuss. Yeah, so we can talk also about extensions to theories with less supersymmetry or other AdS spaces. It's not necessarily just a bookkeeping thing to do more general examples, because as I said, the spectrum really depends sensitively on the parameters that you compute from the Volk solution. So I couldn't tell you, for instance, whether the Klebanov-Strassler type setup would give you the same kind of spectrum as n equals 4 super wells, for instance. So, or perhaps other AdS spaces and other AdS black holes. These are directions that are natural to study, especially if they supply predictions for strongly coupled quantum field theories, if that is the perspective. So we could also include non-perturbative corrections, such as higher genus topologies, D-branes, string type effects. For various technical reasons, these seem rather hard, but I think this is a natural thing to at least begin thinking about. How do we, in this specific example where we have a lot of control, you can compare things to the gauge theory side, how do we include this? It was shown that higher genus effects don't affect the index. So this is something that you really have to see in the partition function itself, if you want to include. And also we just talked about the other. So I think that's all I wanted to say. So are there further questions or do you?
Yeah, just if there are questions, go ahead.
Hi, yes.
What did you mean when you wrote down the partition function? You said there's no topological term present. I didn't understand what that meant.
Yeah. That it's not the topological term that. Where did I? Oh, here. This clicker sometimes goes a little too fast or slow. So this might not be actually the right slide, but had there appeared right here an e to the I theta n, something linear, something imaginary and linear in some theta parameter, where theta is some number that gets spit out of the computation. That e to the I theta is like saying you're weighting different saddles in this sum over n by some additional phase factor. So you're sort of adjusting the holonomy, and that's like turning on, from the two-dimensional gravity point of view, that's like turning on a theta integral of f terms. So it's whether or not you have this first term class showing up in the bowl or a theta angle on the boundary. And if you have that theta angle there, it can be 0 or pi if you want charge conjugation invariance, and if it's pi, then the spectrum gets shifted by half integer amounts and it changes predictions about the gap and so on. So you might have thought that a theta angle could have been generated because we had a Trent-Simons term in the bulk and so on, but it appears to have not shown up there. If we did find a theta angle, it would have changed the value of the index. So the fact that the index matched was a good clue that we got the correct answer. Yes.
Just to follow up on another aspect, just as a point of information, you can actually see quite easily in certain kinds of matrix models that some of the phenomena that you're seeing here can be captured by a matrix model. So you can, for example, add fully non-perturbatively extra branes that sort of live at E equals 0, and that's your BPS sector.
Right.
And then as you dial that up, you see that the rest of the spectrum generates a gap. Those branes sort of repel those away, and it looks like very much like your diagrams where you have a gap developing, which depends upon, yeah, exactly. So
I mean, I think you're talking about the matrix model branes, but I think there's good reason to believe that these guys are also, well, let me not say that, some D3 branes collapse.
no, but I think it's the same thing.
I think it's literally the same, yeah.
Exactly, yeah. So I'm just saying,
it would be very interesting to discuss.
yeah, I'm just saying that the ingredients are available in matrix models, and maybe the right ingredients put together could get exactly the kind of partition functions you're looking for.
Yeah. I think that's very interesting. And this is in principle something where you can go on n equals 4 and check everything in the 4-dimensional theory. So there should be several different ways of seeing the same results appearing. Yeah, it's very interesting.
Any other questions? On Zoom, perhaps? All right. Thought we had a number of questions during the talk, so let's thank Matt again for.